And the paradigm here is imagined movement detection. Okay, on slide 1, now slide 2. Yeah, I have a crash here. Yeah, okay, slide 2. Remember, this is a sort of scheme we're using from Michael Lebedev's paper. I'm still using it because it is sort of, you can a bit mock about it, because he is, of course, someone who likes to work on invasive stuff. And yeah, this is non-invasive. It's not very well developed. That's the least you can say. But okay, we are still on the now on invasive parts. So yeah, if you look at non-invasive BCI, you have different paradigms. We're going to discuss a few of them, the most important ones. So imagine movement detection. There it is. This is what we will be focusing on. So you imagine that you move a limb, but there is no actual movement. So just imagine that you're moving a hand, an arm, a finger, a foot, a leg, whatever. Okay, and then other types of paradigms, like the visual evoked potential. So we will dedicate a lot of attention to it, because this was the first paradigm that entered the BCI field. Event-related potentials are actually overlapping with it, as we will see, and that's another paradigm. And then you have something weird, which is error-related potentials. When you make a mistake, there is also potential related to that you can pick up. So it's sort of a gimmick. Okay, we're going to look at the imagined limb case. On slide 4 now. And this shows a bit also the evolution, because coming up with technology that can mimic movement of limbs is of course very interesting for the paralyzed individuals, right? So to get grip again on life by having a device like a robotic arm perform the tasks that you're unable to perform anymore. But it has seen some evolution. Remember, in the first class, I showed the Hollywood case, where Dr. House had a nice solution for this paralyzed person, and that person needed to imagine, after quite some training, figure out by himself how a cursor can be moved upward or downward on the screen, and then there was a yes/no answer, and then his wife came into the room, and he could answer the question, her question, "Are you still there?" And then he could say yes, remember, and then the tears came. You remember the video. So this is actually referring to how it went in the video initially. Initially, the subject had to figure out how to get control by doing whatever it takes to get control. And that, of course, of time, you need to go through a lot of subject training, and there was also some reward paradigms, an operant conditioning paradigm, as in case of neurofeedback. So you try to do something, you see the outcome of it. If it's successful, this sort of reinforces what you're doing. The second point here is when machine learning was kicked in. If you can use machine learning to extract the patterns and the signatures, you can do more. But then the flip side is that you have to adopt a particular paradigm so that you can get labeled recordings. So recordings that correspond to class A or class B, class C, class D, whatever you want to distinguish with your machine learning algorithm afterwards, after training it. This is another way of doing it, but the big advantage is, of course, that you don't require these long training sessions of your subjects, and this is also leading to much faster turnaround times and better performance at the end, as you will see. So in case of the imagined or executed movements, it's a paradigm that is modulating the mu band. We already have seen it. The mu band is activities going up or down when you perform or imagine performing movement of a particular limb. And then the last, the third, there was also a step forward where you could actually pick up not only the performing or the imagined performing of a movement, but also the planning, the thing that comes before the muscle contraction. So the planning of the movement, that has also a signature in terms of EEG, and this can be used picked up as well after proper machine learning training. So we're going to first start with the voluntary case, slide 5. So we have to go back like 20 years or so, where David Wolpaw was one of the first to show that, and I think he was one that advised the Hollywood movie series there, Dr. House, how it can be done, that people can control certain features, certain signal features of the recordings. So you can, after training, change the normal relationship you have between brain activity and brain functioning and resulting from brain activity and EEG that picks up that activity. So normally when you have EEG, it reflects brain function, but of course that activity is not necessary for, I mean, what you're recording is not necessary for that function, right? The function could be supported in other ways or used in other ways. And this is what you're tapping into. You can actually train yourself to control particular signal features, and this can be differentially picked up by EEG and converted into a signal with which you can control or communicate what you want to do. So slide 6, this is at the Wadsworth Center in the US in Maine. And it relies on what we already said. So the mu band and the beta band, these two bands are connected. So if you have motoric activity performed or imagined, there will be changes in those bands. And this is what you're going to use. And you're going to record over the sensory motor cortex, because as I said before, it's not only motor activity, but also sensory activity, the touch. If you perform an action, the fact that you will touch the object is also activity, of course, in the brain, and you know, the looking forward to touching the object, it already is giving rise to activities in the sensory cortex, in the somatosensory cortex. So these rhythms were chosen by these researchers because they produce activity that can be related to movement, and also that their amplitudes can be controlled after training by the subjects. And then, they try to map using some regression. They can map the activity in these mu and beta bands to control a cursor, for example, on the screen. So slide 7 shows the setup. So you are recording centrally over the brain, because above the motor cortex, you get your signal there, and then the signal is being digitized, sampled, and then you extract the power spectrum from that signal, and you look at, for example, changes in the beta, and this is the mu band and the beta band, and you use that for controlling a cursor to go to a particular target. So that's the idea. In the one-dimensional case, this slide 8 is the most simple one. So you have to advise your users to explore not only motor imagery, but maybe other things like playing chess or playing tennis, whatever works for you to get control. Control meaning, in this case, to modulate the power in the mu band and the power in the beta band. So if you can make a drop, for example, then there is maybe the left target you want to select. If it goes up, it's maybe the right target. So it's a sort of binary control. On the bottom you see the corresponding traces. So you can't pick up that. Of course, if it's one-dimensional control, you will focus on the most powerful one, which is the mu band. I'm on slide 9. and yeah, the video account show. But there, if you this stupid technology. Wait, I will try to do it if it works. No, yeah.